Sound check. Sound check. Alright. Hello everyone. Welcome to the welcome stream where we will continue where we left off last time. We've made a lot of progress last time and our renderer was running significantly faster when using mesh shading pipeline. We had some sort of unanswered questions, not questions, but we were testing this on some meshes, and on some meshes backface culling worked well, on some meshes it didn't. I looked into it a bit and I know what's going on there. And also we will sort of rush through the part where we make the rendering faster by doing some performance optimizations. Some of them we have talked about on stream before. Some of them I said, hey, I kind of need to do this at some point, but I don't want to do this now, so the point is now, right? And then we'll see if we have time left. Tomorrow I want to start rendering more meshes in actually like different locations on screen. And if we have some time left today, then we'll kind of prepare for that. And if we don't, then we don't. Let's see where we left off last time. It should be basically yeah, so we can run our program. It can render a mesh. We should be able to run a program and release. It should render the other mesh. Yeah, and let me enable the let's first deal with the sort of clustering problem. So yeah, I think that should be enough. So as you can see, our culling is kind of inefficient right now, right? We on this mesh, on the kitten it worked fine, but on this mesh, on Buddha mesh, we can't cull too many things. So the issue is I don't have my drawing equipment set up because I didn't think I'd need to do that. But the issue is basically that we were kind of being sloppy when we were reducing the vertex size sometime earlier on stream, and we were using a half precision format, which is not a great format precision wise in terms of like it uses 16 bits, but it doesn't actually use them very efficiently. You should be able maybe to see, I sort of see this on screen, I don't know how well you can see this, but the surface around the mouse cursor, well, it's not clearly, I guess it won't be clearly visible, never mind. But so the problem is that half precision kind of destroys our mesh a bit, and the result of that, let's see if I can, yeah, I'll just sort of draw with my mouse today because I won't really draw much. So there's two problems that happen. The first problem is if you have like a triangle mesh like this that may be reasonably planar in terms of the normals, right? Well, with the pen it's much easier. Half precision significantly distort the vertices, so what could happen after half precision is the mesh becomes kind of like this in some local area, and that significantly, that makes the triangle orientation significantly worse in the cluster. The second problem that may happen is if you have a small triangle, and these things can happen on like areas where triangles are so small that it's hard for us to see them right now because we can't like bring the camera closer to the mesh, but they do happen. So the other problem that can happen is if you have a triangle, half precision may collapse all of the vertices of the triangle to sort of the same point. And actually, if I look at the code that we wrote last time, there was a thing that maybe I said before, maybe I said on stream, maybe I didn't, I don't remember, but it's like, hey, we are computing the normal of the triangle, and then we are normalizing the normal of the triangle. And if the area of the triangle is 0, It's kind of weird, but these things shouldn't really happen. Turns out in this mesh they happen a lot. We can let's figure out how many zero area triangles we have. And if the triangle is really close to zero area but not quite, then some computations may destabilize. So basically, it's not good for precision all around. So yeah, so we have like 35,000 triangles that are zero area, so that's like what, 3% or something, which is not great. And then because they're zero area, some of these computations don't work well. So there's like a bunch of problems with this code because of half precision. So what I want to do for now, there are better ways to compress the vertex data without using half precision, but still using 16 bits of position data, and we'll get back to compressing vertex data at some point on stream. But for now, I just want to say, hey, let's undo this and, you know. Oh, and by the way, right, when you run the program right now, it says here how many meshlets we can call. So this is like 2%, whatever it was. So this is really not good. So let's just remove this half stuff for now. It wasn't actually helping us performance-wise that much, and we do have enough memory right now to be able to load the entire mesh. So for now, let's just remove this. We will come back to this at some point, but not today. So I want to change the vertex back to use floats. I only need 3 floating point components. Do I have half math left anywhere? For texture coordinates, we'll leave this as is for now. And yeah, we don't need to decompress things, and maybe that's enough. Right, so now you can see that our calling called way more triangles, so that is nice. So now we are calling, so this is about 20%, right? Yeah, so this is 20.4%. So this is kind of what I was hoping for originally, right? This is a pretty large mesh. It should get 20%. So our technique does work on high poly meshes. It's just that half precision was kind of destroying them. So the other thing is there are better ways to compute these cones. And I have researched some of this stuff over the week. And some of the... there's some stuff that is like documented somewhere. There's some stuff that isn't. I don't want to go into too much details about this now because A, I kind of want, about some of the stuff I want to write a blog post. B, all of this is now available in the mesh optimizer library that we are using. So what I want to do is I want to update, I guess I want to commit the non-half precision first. Oh, we still have the zero area. Wait, what is this? Oh, right, okay. So that's the first simple thing that we are doing. This is day 11? I don't know. Oh, day 9. Okay. Alright. Day 9, remove half precision for positions. For now, we just decompress positions. Compression is interfering with the efficiency of cone culling. And once again, this is not a problem on meshes where triangle density isn't just so high. Like on Kitten, it wasn't really a problem. But I want to reset back into like a good state, right? And then when we do compression later, we can evaluate directly what kind of format we should use and how much it penalizes the cluster calling. Alright, so yeah, so the other thing is if you build these cones better, you can get better rates. And so this was 20.4%, and now I want to switch to the algorithm that I implemented in Mesh Optimizer. What? Great. I don't know. Oh, Right. Yeah. So we've updated the submodule to the latest version. And now I want to just change the code that we were using to use the library. The thing is, the library interface. I mean, I can just do this. I can just do this here. It will be easier for us if we also switch the meshlet generation code. So yeah, for now, let's do this. Oh, but we have like 3 functions for this. Let's remove this function for now, and then we'll just merge these two. And the reason why we want to merge these two is because I want to use the, I basically want to just replace all of this code with the stuff that's available in Mesh Optimizer, because it's better, faster, nicer, etc. So there is a function called build. Oh, I guess I should compile the code so that Visual Studio knows that I have updated the library. No, this is weird. Hold on. So yeah, there's like a new set of algorithms that's called clusterizer. I've asked on Twitter if it should be clusterizer or clusterer, and people say it's clusterizer, so clusterizer it is. Although I think Google search reports more results on cluster than clusterizer, but yeah, so there's a function called build meshlets now in Mesh Optimizer, so let's just switch to that. And the actual meshlet generation algorithm is the same thing that we have built on stream. Basically, it's like slightly cleaner, but it's not any different. The cone generation algorithm is substantially different. So I think we are still, oh wow, I think we are still doing like 6426, so let's do that. Oh. And then you can call this function called build meshlets with, you can pass it the sort of target where you want to generate the data and the source indices, count, number of vertices, and then max vertices, max triangles. And that gives you the actual number of meshlets. So we'll use this to resize the vector. So this basically replaces this bit. Now we still want this code that rounds the number of meshlets to 32. We will remove it later, but for now we still need it. Oh, I guess this is the thing. And you know, this structure will be familiar because this is the same thing that we were doing on stream. This seems convenient and seems like the sort of roughly right kind of thing. Now, instead of doing our makeshift cone generation, we can... Oh, right, so we still need to fill sort of our meshlet structure that currently is roughly the same, but we will change this later. Build meshlets. So for now, we'll just copy these fields verbatim from the other struct, but we'll change this momentarily. So yeah, meshlet size. So basically, we need to build like the meshlet structure that is mapped to the GPU directly. This will go away, so for now I'm just using non-descriptive name. Oh, I guess I could have... Right, I was thinking about something else, but... So yeah, for now, let us just say that we will copy all of these data directly. The layout should match exactly. The, I guess, coding style is different between the two libraries, between the library and this demo. Yeah, anyway, so the reason why we did that is, I mean, I wanted to do this anyway, but now we can call a function called compute meshlet bounds, that given a meshlet and given the positional data, which should be in floats, but we've just unpacked it, so it's already in floats, so that's nice. So that is the pointer to this guy, and vertex count, and size. So this gives us a structure that has the cone data that we have discussed, that we have computed before, and also some auxiliary stuff that we may start using, but maybe not this time. And then there is some formulas. This is the formula that we are already using. It's correct for orthographic projection. Oh, one other thing that I did. So last time I kind of hand waved around the issues with perspective projection, but I had to actually research this more closely, and the math is substantially different for perspective projection. And there's kind of two variants that we can use, and this comment goes into detail. This math is very interesting, but I kind of want to write the blog about this, so I won't go into details today. And for now, we're using orthographic projection, so for us, the same thing that we were doing last time still works without issues. So yeah, now I don't need all of this, like all of this. And I should be able to just copy data from the bound structure. Let's see if that worked. Clearly didn't. Oh, 0. Oh yeah, I always forget to do these things. Oh, wait. Oh, here. Alright. So we still are rendering the mesh. It's still called. Let's look at the like culling rate. So now it's 23%, right? So yeah, so this is because the library that the algorithm in the library that I wrote is way more careful about how it computes the code, which in this case gives us an extra 3% of triangles called, which is nice. Alright, so that works. That's great. And now our code is substantially shorter, right? This is the entire function because we are using like algorithms from the library that do the heavyweight work for us. So that is cool. I want to commit that. I have to flip between culling states every time, but day 8 switch, oh, day 9 to mesh optimizer for meshlet cone generation. This gives, this improves the rejection rates on Buddha from 20% to 23%. And cleans up the code, which is nice. Alright, so okay, so now the next thing that I want to do is I want to measure the performance that we are getting right now and see about making it better, right? So for that, we need to start looking at the GPU time. Last stream there was a very helpful comment from Christoph Kubish from NVIDIA that I should try to disable vsync, because right now we are running vsynced. Like you can see our CPU time is 16 milliseconds. Our GPU time is measured separately, but you can see it's fluctuating. So apparently, for some reason, if you disable vsync, the timings become basically rock solid. The problem is, so this is how we right now enable vsync, right? And to disable vsync, you should do this. So the problem is, this value might not be available, right? So you have to ask, like you may not be able to use immediate mode, so it could be that you run on a system where the only available mode is vsync on, right? However, in theory, there's a way to query the available modes, sort of similar to how we do some of these other swap chain bits, where you can ask the device, hey, what can you use? And it'll tell you, yeah, you can use immediate, or you can use FIFO or whatever. But NVIDIA, and we will not spend time trying to do this because I have already tried to do this. NVIDIA is an interesting adapter. On NVIDIA, you can use immediate. However, if you ask the device, do you support immediate, it will tell you no. And because of that, even if you ask the device and then like do this, validation layers will be upset because you're using something that is not claimed to be supported on a device, but it does work. So that's kind of weird. So, yeah, let's do like, yeah, I don't know. Let's do this. Oh, is this? Oh, this is like a runtime thing. All right. Let's just. Come on. What? Oh. Yeah. Let's just define the thing, and then this will be the same like kind of thing as we do like here, where it's generally 0 or 1 or whatever, but we sometimes need to switch it to do profiling or debugging or something. It's unfortunate that we can't cleanly ask immediate, and I haven't looked into why this is true, why NVIDIA is doing things this way. Oh, I guess we can just do so let's do this for now. Oh wait, this was backwards, sorry. So vsync is FIFO and immediate is do presentation as quickly as possible. So if you disable vsync, then we should see GPU time as being stable, right? So it now basically is 0.08. So that's good. Now we want to see A, if we can improve this, B, like this number right now includes clearing the screen. Clearing the screen is fast, but if your entire frame time is 0.08 milliseconds, then you know it may be a substantial portion of that. So let's do the same thing that we did last time. Oh yeah, we already have this, which is we'll render like 100 meshes. Right, so with one mesh the GPU time was like 0.08, although this could have been rounded, and with 100 it's like 7.3 or 4. It still fluctuates a bit, but it's nowhere nearly as bad. Oh, the other thing we could do is we can enable stable power state. Maybe that will make things even more stable. I forgot how that works. No, it still fluctuates. The thing we set stable, so you can notice right now we are running at like 8.2, and this is because I ran set stable power state, because set stable power state, it tries to fix the GPU clocks, but it fixes them at a slightly lower value because it says, hey, this is the power state that the GPU can run on indefinitely. So we are not measuring the peak performance of the GPU, we are measuring the sustained performance of the GPU. And in some cases, it's correct to do one, and in some cases, it's correct to do the other. But we want to run fast today, so let's run without stable power state, and we are running 7.3, 7.4. The other thing I wanted to do is, now that we have all of this amazing information, yeah, a few people have pointed out to me that RTX is not the correct name for the stuff that I'm doing, which is true. RTX is referring to NVIDIA's ray tracing, and we are not doing ray tracing. But we are using a thing that's available only on NVIDIA RTX cards. Anyway, so let's switch that. So yeah, so let's add a metric for the number of triangles per second that we are rendering right now. And we will measure them in billions because we are rendering a lot of them. Otherwise known apparently as gigatriangles per second. So that's interesting. Alright, so how are we gonna compute that? So we are rendering draw count meshes. Each mesh has that many triangles, right? And we are rendering them in, and I should do, I guess we are on 64-bit, none of the stuff can overflow, but in 32-bit it can. So yes, now we need to divide by the number of seconds, which is frame GPU, and we are measuring things in milliseconds, so that's number of seconds. And then we need to get billions, we need to divide by a billion, right? So it should be this, e minus 9. Alright, yeah, so this seems relatively accurate. It's noisy. Let's see, that probably won't help because it hovers. Yeah, okay. But yeah, so we can render around 15 billion triangles per second right now with mesh shading, and without mesh shading we can render about 7.7, right? So right now we are about twice as fast with mesh shading pipeline than without mesh shading pipeline. I do not know why that is. It's slightly counterintuitive. We are appearing to be hitting some sort of hardware limit with traditional rasterization pipeline. Like even if you disable culling helps, but it doesn't help that much. It doesn't help 2x, right? So yeah, we're running into some sort of limit. We don't have NVIDIA profiling tools working, so we can't really profile anything anyway, right? So, but it doesn't matter, we are running faster, way faster, so that's nice. So now I want to see how can we get even faster than that. So there's a couple of problems that we have already discussed, and I just want to fix them. The first problem is this. In the task shader and in all other shader stages, really, in the task shader and in the mesh shader, right, we are reading data from this meshlet structure. So this meshlet structure has several problems. Problem number one, whenever task shader has to call a meshlet away, it has to read this cone data, but it has to skip past all of this data in memory, right? Because our memory layout is there's like a cone, which is 16 bytes, and then a bunch of stuff, right? This is not a great memory layout, right? What you want is you want a meshlet structure that's pretty small. Like maybe you just want an array of these guys, but that's kind of a bit short-sighted because we will want to do occlusion culling and some other types of culling, and it's not clear that you want actually giant parallel arrays. But you don't want this data for sure. And this data is large, right? So this is 256 bytes, and this is 384 bytes with these things. So this data is large. So that's the first problem. The second problem is we are kind of allocating space for 126 triangles in our memory layout, no matter what. I forget what the metrics on the on different meshes are, but I feel like for that Buddha mesh we were hovering around 90 triangles or something like that per meshlet. So this means that we are wasting like 100 bytes or something like that here. And this probably also is a small cost on memory bandwidth, probably not that substantial, but we are still skipping things, so that's also not nice. And the final thing is that we are not using, so there's this to-do comment here. Oh yeah, there's like two to-do comments here. So the one more thing is that most of our meshlets have 64 vertices, but if you have fewer than 64 vertices, then this loop goes for example, 2 iterations for some threads in the warp, and for only one in 1 or 2 threads. And this is not super optimal. I don't know if we actually pay any cost here because of this. It could be that we don't, but we'll see if we can fix this and make things faster. And the final thing is, there was this intrinsic that we tried to use on stream really early on. It wasn't making things faster for us, but as we discovered last stream, we started getting huge gains from mesh shading when we enabled task shaders for unclear reasons. So I'm hoping that this time around, we were limited again by some weird hardware quirk, and now we aren't, and maybe now this thing will make some difference, right? But we are basically trying to make sure that everything that we do optimally. So, which is to say, oh, and for this guy to work, you have to pack your index data in 4-byte chunks. So all of this says we need to rework how we structure our meshlet data. So what I want to do is I want to split the meshlet data in 2 kind of things, right? And I will do this on CPU side first. I mean, I'll have to do this on both sides equally, right? But let me explain. Let me like write up the structs first on the CPU side. So here's what I want. In the mesh, we are right now doing this, right? So what I want is I want to take this data and move it out into a separate array. Now, right now, this is arrays of 4-byte integers, right? This is arrays of 1-byte integer. But, as I just said, we kind of want to pack these things into 4-byte units anyway, because we want to use this beautiful intrinsic. Oh, but then the problem is we will not be able to tell if our beautiful intrinsic actually saves us time. So that'll be unfortunate. Let's check right now if the beautiful intrinsic saves us time. And then if it does, regardless of whether it does or doesn't, we'll do this anyway, but I just want to see. I haven't really benchmarked this intrinsic in isolation after all of these changes. So we already did this last time, but what you can do, not last time, on some stream, what you can do is you can say, let's see. So I want the maximum number of triangles to be divisible by, I want to fix the comments because this code is going away like right now anyway. But yeah, so I want to have up to 124 triangles because that's divisible by 4. So I don't have to think about padding or any weird stuff like that. Then I can switch it here, it's sort of less important. I should switch it here, this is more important. So that should just work. All right. And then instead of, I sort of wish GLSL had unions, but it doesn't. So what we want is we want the same data but in 4-byte units. We don't need this data anymore. And now here, instead of this, we want to use this intrinsic. Oh, and we want to change this loop. So it's like index group count, I think we called it last time. Index count plus 3/4. We pad the number of indices up to the next 4-byte boundary so that we copy out all of the data, and then we want to write I is the byte offset. No, I is not. I is the 4-byte offset, so we need to do I times 4 for where we are writing the data, and then we need to do meshlets my indices packed I for what data we are writing, and this should just copy data in 4-byte units. Let's see if that actually worked. It actually did work. Aha, yeah. Oh, now it does help. Nice. So now we are running at like 19 point something, who knows what, right? 19 billion triangles basically per second. So yeah, so this intrinsic was super valuable. Now it makes sense why NVIDIA included this. And the reason why we weren't seeing benefits from this is because we were limited by something else. Who knows what it is. So that's cool. And now we just need to repack the data, and hopefully this gives us a bit more performance. So we did that. Don't need this to-do comment anymore. We didn't do that yet, but that we can do later. This probably will not help because we're probably losing so little time on this that it doesn't matter. And this is up to 100.4. Actually, yeah, let me commit this first before we start messing. I guess to commit this, I probably want to do now every time I commit, I'll have to do this vsync dance, which is fortunate. Day 9, use the intrinsic with a name that I always forget because it's very long. Alright, so now let's repack the data. This hopefully will save us a bit more time. So what I want on the C++ side, now that we know that we actually really want to use 4-byte sort of index chunks, right? I want to just say that this data is 4-byte integers. This data is like 1-byte indices, but it's really 4-byte integers because you kind of want to read things like that anyway. So I want to build 2 arrays instead of 1. There will be an array of meshlets, and there will be an array of like meshlet data or something like that. And the second array will just be 32-bit values, right? That will be either vertex indices or triangle indices. At some point, we might decide that the vertex indices should be 16-bit integers, in which case we'd have to repack the data again, but it doesn't take that much time to do all of these things, so I just want to do this now like that. So now we won't need this data here, because this data will be stored here. However, we will need to store an offset into this data, right? And I just want to store one offset. And the way data, because I mean, there's no particular reason why. You could store 2 offsets, but 2 offsets require more data. But basically the assumption will be that data offset plus vertex count minus 1 stores vertex indices, and then we store indices packed in 4-byte units after that, right? And that's basically it. And that's basically it. So now our meshlet structure is 32 bytes because this is 16 bytes and this is like 6 bytes, and then there's 10 bytes of padding. We can actually use, we will try to use the other representation of a cone that Mesh Optimizer library now computes. Maybe that'll make some difference for performance, maybe not. Okay, and now we just need to fill this data like that, right? So, the way it works is that we store the data offset, which is basically the current size of the meshlet data array, and now we want to start packing things into this meshlet data array. So for each vertex, for each vertex, we need to store vertex index in that array. Yeah, and then we need to store index data, but index data we need to store in 4-byte units, right? And we need to store, if we, for example, have only one triangle, this is just 3 indices, but we still need to store one 4-byte value, right? So, I mean, yeah, index, let's just call it index group count, same thing. It will be meshlet triangle count times 3, which is the number of indices, plus 3/4 to round it up and, you know, divide. So this is number of 4-byte units that we need. And then we'll just say, hey, we need an array of index groups, which will need up to max triangles times 3. It's kind of the same thing, times 3 plus, yeah, plus 3/4. We'll zero initialize this, I guess. Oh, it wants us to make this const. Fair enough. And then copy the actual index data into this array. Meshlet indices. And then we need to copy only the number of indices that we actually have available. So it's like meshlet triangle count times 3. And then everything that we haven't copied, it was zero initialized, so it will just be zeros, right? Which doesn't really matter, because the rasterizer will ignore this, but it's sort of nice for debugging. So we don't need this anymore. We've already done this. I kind of want to do this. Now I kind of want to do this. Right, now the code is nice and clean. So yeah, so we fill all the vertex data. Oh, oops, I forgot to actually. We fill all of the vertex data, then we sort of assemble the indices from the meshlet in 4-byte chunks. We could read 4-byte values directly out of this array, because it's C++, C++ can do anything, but it may be slightly cleaner this way. Maybe it doesn't matter. I don't know. Maybe it doesn't matter. Index groups. You know what? Maybe it doesn't matter, and maybe we should just Something like that. Okay, so in theory now we are packing things correctly. We have not changed our shaders yet to do this, right? Because our data format on the C++ changed, but I think this code works. I mean, it should work, hopefully. So yeah, let's change the shaders now. So on the shader side, we want the same thing. So we want basically this. And then we want a second array. Right, which we'll call meshlet data. And this will just store unsigned integers like that, right? Now in theory our shaders will just not compile, and if we just fix compile errors, then we are almost done. There's one more thing that we need to do, but right, so instead of reading vertex indices from the meshlets directly, we now need to get the data offset. So let's do this. So vertex offset is just data offset, right? And then index offset is vertex, well, yeah, let's just redundantly write this out, plus vertex count. I guess I don't know why. Let's do this. All right. So instead of reading indices from the meshlet, now we just read them from the meshlet data, right? Really simple. And then vertex offset plus I. And then here, same thing, instead of reading this thing, which doesn't exist anymore, we just do meshlet data index offset plus I. So that in theory should be good. Our task shader shouldn't care. And the other thing is we need to actually upload this data to the GPU that I forgot to do. So let's look at that. So we need one extra buffer. Let's call it meshlet data buffer. It's the same thing really. And we need to upload that from meshlet data. I don't know why in this, yeah, it's fine. And finally, we need to bind this buffer to the shader. So just add another descriptor, meshlet data buffer. And then maybe code works. There is a warning. Okay, clearly the code didn't work. Oh, I forgot to align. No, I didn't forget to align anything really. Okay, so clearly our code didn't work, and now we need to understand why. So we have a bug in our code. Our bug might be in a billion places because we just changed a bunch of code at once, but it was hard for us to not change a bunch of code at once. Not quite sure where the bug is. Let's switch to debug. Enable. Yeah, this is good. Let's see that we don't have any assertions anywhere or whatever. No. And yeah, our kitten is also not feeling very well. Oh yeah, we forgot to destroy the buffer, which we always do. So that's fine. Yeah, so our code doesn't work yet. Let's try to figure out why. So the first thing is, let's just look at the data that we are generating on the CPU side. So let's see, first meshlet, data offset 0, 64 triangles, 95, 64 versus 95 triangles. The next one is 136. So let's try to see if this is right. 95 triangles should be 95 times 3 to 85 indices, right? And then we need to divide it by 4. It does not divide by 4, but if you round it up, it's 72. So it should be 72 4-byte integers plus 64 vertices, which is 136. So data offset seems legit. And then the first 64 values should be the vertex data, and then the next 95 next sort of, yeah, however many that was, like 32, right? Or not 32, sorry, like 72, should be the indices. Let's see if that's right. So the first 64 values look like small integers, and then from 64 on we start to see large numbers up until 134. Oh yeah, 100. Yeah, okay, that's correct. And if we do hexadecimal, we can see that the bytes here is that right? Yeah, I think that's right. Yeah, so like the first value like this, right? So this one, this says, hey, 2 to, oh, they're ordered from, it's like little endian, so it's 0, 1, 2 first triangle, 2, 3, 0 second triangle, 3, 2, 4, 5, 0, 3, etc. So seems okay. Seems okay. So what else could go wrong? We did upload the data, and I mean, clearly we have a kitten sort of rendering, it's just not fitting very well. Our data layout on the shader side might be broken somehow. I don't know if that is true. Let's do this for now. Let's switch to 32-bit integers and then explicitly add padding. And then do the same on the C++ side. Oops, no, wait. Alright, so that didn't help, clearly. What else might be broken? It's unfortunate that we don't have a debugger to debug this. Let's try to only render the first meshlet. For that, let's just say that we are only spawning one task, and we, in the task shader, we disable culling, and then we only spawn one task. And the good news is it doesn't flicker. The bad news is I'm pretty sure this is not how a part of a kitten is supposed to look. So it looks like even the first meshlet is broken. All right. In the absence of the debugger, like the only thing you can do is to Oh yes, okay, all right. On the C++ side we have vertex count first, and then on the GLSL side we have triangle count first. So that's not great. Okay. Alright, that looks more like a small part of a kitten. Now let's undo this. And then draw tasks or tasks and V or something. Yeah, okay. Meshlet size over 32. Something like that. Alright, so that looks like a kitten. Okay, that was not too hard. Alright, and now we need to disable vsync again. Should we just like disable vsync and release always for profiling? Yeah, for now we'll just keep toggling this. Alright, we are running sort of at 20 billion triangles per second. I say sort of because it fluctuates. But right, so in this frame we clearly were running at 20.1 billion triangles per second. Alright, let me try to do the... let's try to reduce the meshlet data slightly more, because right now it's taking 32 bytes and it should be easy for us to pack this into 16 bytes. I don't know if this will even help, but we are, and we'll have to add more data to it in the future, so I guess it's good if we reduce the impact of these guys anyway, so let's do that. Let's do that. So yeah, so we didn't really need to do, this was fine. Like it worked without issues, it's just that our layout was broken. Oh, right. This align S will be problematic, but okay. So that probably still works. Yeah, and it's still it's basically 20 billion triangles, but it's not stable 20 billion triangles per second. In some frames it's slightly more, in some frames it's slightly less. It would be nice to have stable 20. I guess we can check if this thing is important. Let's just do this for now. It's kind of interesting that it hovers between 20 and 17.2 or something like this. It's pretty significant fluctuation. Although this guy, interesting. Yeah, why is this hovering between 20 and 17 and this is between 5.8 and 5.7? I thought the delta is definitely larger. So on the GPU time the fluctuation is like 1%, but 20 over 17 is like 10. That's odd. Are we doing things correctly here? Yeah, I think this is correct. Oh, I see, right, yeah, okay. When we compute triangles per second, we are not using the average GPU time, which is smooth over time. We are using the exact time of the GPU frame that happened just now. Okay. I don't know that this is what we should be doing, because this is noisy, right? There's like 10% fluctuation. And okay, I have Chromium running right now. Also, I'm streaming video, which hopefully is still streaming, yes. And I think it's using NVEnc for this. Let us double check. Video output. Yeah, so it's using NVEnc. So this means we are using GPU to encode the video feed, and we are using GPU to render things, and we are using GPU to like display this beautiful web page even though it's in background, it's still displaying. So I guess it would be more correct to use the average. So let's do that. All right, but now we are not 20. We are like 18.7, 19. Interesting. I guess it jumps. Right, it makes sense. If there is constant fluctuations in the frame time, then the average would be displaced. So the average is not really the min. Yeah, okay. But this is a more honest measurement, so that's fine. So yeah, does this help at all? Doesn't help too much. Maybe this is our performance limit, because yeah, honestly, the only other thing that I think we can try to do is pack the meshlets into 16 bytes, but I don't know why that would matter in this case. Like, let's do this, because it should be simple, but I don't know why it would matter. So 4 bytes here, 4 bytes here, 4 bytes here, and we need 4 more bytes. So it's like this. Yeah. I would be surprised if this is actually make things different. And I don't need to do anything here. GLSL really needs to throw an align S keyword. It's kind of important. So yeah, my library already pre-computes 8-bit data for this. Oh, except that it's signed. So it should be really easy for us to just use that. And then here, wherever we use the cone, no, in the task shader rather, the cone, yes, it should be, oh, GLSL is funky, so I should cast this vector to a vector of integers. Well, this is not even a vector, I see, okay. I guess never mind, I can just do this. This is painful. So let's see. And then same thing. Let's see if that works. It doesn't work. Oh, I guess GLSL doesn't support C++ like constructors. Yes, okay. Yeah, it's basically the same, or maybe it's a tiny bit slower. It's hard to tell. So the good news is we, with default rasterization pipeline, we are running at like 7.5 billion triangles, and with the mesh shading pipeline, we are running at like 19. Before this change, at least. Let's undo this because it doesn't seem to help. We might do this later when we repack cone data. For now, we just don't seem to need this, which is expected. But it also requires us to do this crazy manual padding because I want this thing to be 16-byte aligned. So I guess for now, let's just say it was a bad idea. Wait. Okay. So the good news is we are running. No, I guess it's the same really. I see. Yeah, basically it doesn't seem to matter performance-wise in this case, where the meshlets are 16 bytes or 32 bytes, which is sort of expected. Anyway, yeah, so we are running at almost 19, maybe 18.8. So this means we are running 2.5 times faster than a traditional pipeline, which is really good. I was hoping to get to 20. I think I was getting 20 in my earlier tests. And we are getting 20, it's just that it's not 20 average, it's 20 like peak. Oh, maybe right, maybe if I wasn't streaming, okay. I think streaming probably eats like a billion triangles per second or something of our performance budget. And that would actually make sense. Because we are running without vsync, so basically we are saturating the GPU. Okay, yeah. So let's just call it 20 billion triangles per second when we are not streaming, and 19 when we are, which... okay. Is there a GPU load somewhere here? Right, GPU load 5%. Let's see what that does. Well, we are running at 90% GPU load. So yeah, so I think without streaming... Well, right, we are running at 90, but our CPU time is like a millisecond larger than the GPU time, because we run them in sync. Which is a delta that seems too large, but maybe that makes sense. So yeah, maybe if you actually don't wait for GPU when you launch workloads, we would be running at 100%. And I think if we don't stream, or if I switch the encoder to software encoder, not NVENC, which I don't want to do right now because it will probably terminate the stream, but that should get us to 20. So we're almost at 20 billion triangles per second, not quite, but this is fine. And that's the optimization part that I wanted to do. So to recap, we have improved our cone calling by using better algorithms. We have disabled for now half precision stuff so that large meshes don't explode, or rather don't, so that culling is actually effective on large meshes. And we have repacked the data so that it's way nicer for the GPU to consume. And we've used this amazing NVIDIA intrinsic that now actually helps us. And as a result of all of these, we are running at almost 20 billion triangles per second on this GPU, not quite because of streaming. With a 2080 Ti, you can probably run faster, right? I don't know how much faster 2080 Ti is supposed to be. It's probably like 30-ish%, I would guess. Because I think 2080 was supposed to be roughly similar to 1080 Ti, and 2080 Ti was supposed to be like 30-ish% faster. But it depends on the workload. I don't know in this workload what the results would be. So let's commit this, because this is good. Day 9, repack meshlet data. We are now splitting meshlet in this vertex index data from meshlet header data, we already submitted the intrinsic earlier, right? Which gives us a bit of an extra performance boost. When streaming, we are now rendering Buddhas at Happy Buddha at 90 billion triangle per second on 2080. We should be able to get to 20 billion triangle per second without NVENC overhead. I'm assuming this is what's going on, because I think I did tests that were similar to the stuff earlier, without streaming, obviously, right? And I think I was getting 20. Let me think if we can do something something else, really not super simple necessarily, but can we do anything else to make this go faster? We still have this to do comment, but we'll deal with it a bit later. Yeah, I don't know if you can do anything else easily. Like, we could try to pack the vertices again, but then we'd have to undo we'd have to actually pack them with non-halves, and that'll be slightly painful. And who knows, this probably will not even help. Oh, here's a simple test, I guess. Does performance change at all? So right now we are using 24 byte vertices. No, 20 byte vertices. So this is 12 bytes, this is 4 bytes, and this is 4 bytes. We aren't actually using UV data, so here's a simple test. Do we care, right? Does performance improve at all if we shrink our vertex data in this specific case by 20% and make it 16 bytes aligned, which actually might be important. I thought there might have been some NVIDIA thing where reading from storage buffers. On earlier NVIDIA generations, you should really try hard to align storage buffer structs to 16 bytes, I thought. But maybe it doesn't matter on 2080. But yeah, here's the really simple test. We aren't really using this anyway. Right. Well, apparently we are using it. How are we using this? Oh, we are like decoding it but not using it, okay. Oh, and the same thing happens in the vertex shader. This one. Oh, and now I have to enable vsync again. Damn it! Vsync. Yeah, so this looks like it doesn't really matter, or maybe it made things a tiny bit faster, but not really, right? Since our timings aren't rock solid stable right now anyway, it's hard to tell, but it seems like it doesn't really help. So, yeah, I don't know if you can do anything else right now. Like, this might be basically speed of light. Like, in theory, you can do some extra culling that's per triangle inside the... So, we can do more things. So, you can, in theory, do some extra triangle culling inside, per triangle culling inside of compute shader. You can do a slightly better job, maybe, at determining the clusters, or the meshlets, rather, which may buy you like an additional, you know, like 5% or 10% or whatever it is that we need to get 20 on stream. But that is like giant R&D effort. I don't know how to do this right now. In terms of things that I know how to do right now, I think we might be done with the getting a giant mesh to render as quickly as possible. Because yeah, I just don't know what else we would be able to do. Everything is in the GPU memory. We are like doing 100 draw calls. It could in theory be the case that we are losing slightly, ever so slightly, on the number of, on like 100 draw call dispatch. But honestly, it seems impossible. Let's try to fix this. So we'll draw 128 Buddhas. And this thing drives me nuts. Let's just do yeah, cause I'm tired of switching this thing back and forth while we work on performance. What? Wait. Hold on. Oh, well, yeah, okay. Hold on. Let's do this again. Okay, so now, I mean, I just don't see how this is possible, but let's just make an experiment. So now we'll render one draw call where we dispatch 128 times like the number of tasks, task shader, task warps that we were issuing previously. And now in the task shader, the index, whichever index, this index, yeah, this index is now like 128 times larger. So if you do this, we should be able to have the same like data rendered. Oh, it's not percent, it's, we have to mod it by the actual number of things. Alright, how many meshes do we have? 11296. Well, oh, that's for shoot. Okay. Oh yeah, that's correct. Right. Yeah, no, that's exactly the same perf, right? Yeah, I mean, I thought as much. I think when we were drawing kittens, we probably were losing some amount of time when we were rendering like 100,000 kittens or something, like 10,000 kittens, because the mesh is smaller, but this mesh is a middle and triangle, so yeah, so we're not losing time here. Yes, I don't know. This might be it. I don't know how much more we can, like, what else we can squeeze from this, right? Because honestly, it seems to render fine. Alright. Okay, cool. Yeah, I guess I will not commit this vsync thing, but I need to find a better way for switching the vsync for profiling. A better way than just switching it on and off, which is not healthy. Alright. So that's cool. So we are running much faster, and this is the main thing that I wanted to do today. But I want to spend the remaining time, and I guess today can be a slightly shorter stream than usual. But I want to spend a bit more time on preparing. So what I want to do tomorrow is I want to start rendering more things that are actually visibly distinct on screen, right? And I kind of want to start using a perspective projection and a depth buffer and stuff like that. Because right now what we've been doing basically was we've been experimenting with these amazing techniques, but we still don't have a more like real world setting where there's a depth buffer, there is perspective projection, you can actually render multiple things on screen and see all of them at once. Right now we are rendering 100 models of Happy Buddha, but they are all overlaid on screen, so you have to promise me. In fact, I have to promise myself, trust me, I have to like trust myself, right, that hey, it's actually 100 things instead of just one thing, because you can't see a difference visually. So we want to start changing this code to work better for that. So what do we start with? What do we start with? Should we start with so we could create a depth buffer. It's somewhat challenging to do. Well, I guess we can just embed it in the swap chain for now. We could create a depth buffer, and then we could set up perspective projection, and then we could do some other stuff. Yeah, you know what? I think it's high time we have used a depth buffer, because you see right now there's like some weird stuff going on here with the mesh, and if I Let's switch to kitten and let's just switch for debug mode. Consider the performance part of the stream over, and now we'll just do some other stuff. In debug, under debugger, we're running 6 billion triangles per second on kitten, which is not too bad. Not too shabby. Yeah, I mean, we are just limited by something else. So actually, you're right, that's an interesting point. Right, so this is the problem that I was talking about with kittens, where I guess we can draw 1,000 kittens. But then the mesh shading pipeline is like tiny bit faster, but not really faster. And I think this is because we are bottlenecking in some other parts because we are not doing things right. Like if you render 1,000 kittens, you probably should not be submitting 1,000 separate like tasks here. And this is what I want to get to tomorrow, where I want to actually see like 1,000 or more kittens on screen and have good performance, like better performance than what we are seeing right now. Because right now we are saying, hey, when you render like a lot of kittens, then you have 6 billion triangles. But when you render a lot of Happy Buddha models, you see like 20 billion, right? So we are clearly losing like, what is it, like 3.5x, 3x, a bit more than 3x of efficiency on something, right? And we don't need to be, hopefully, so we'll try to not lose that. Alright, so let's start by, actually let's not start by adding a depth buffer, let's start by adding, so let's do 100, we are rendering 100 kittens. Let's start by just rendering a 10 by 10 grid of kittens instead of like a kitten in the same place. So to do that, we need to pass extra data to the shader, and to do that, we will use a concept that we have not used on stream before, which is called push constants. Push constants are a way to pass relatively small amount of data to the shader. It is not on some architectures like AMD, the fast path, like the number of things that you can pass to the shader and actually stay on a real fast path is like 16 bytes or something like this. But on some architectures, it's more than 16 bytes. Vulkan guarantees you can use up to 128 bytes on all architectures. But in some cases, like on AMD, if you use more than some small number of bytes, you'll just trigger a slower path. But our code currently doesn't run on AMD anyways, so we don't really care, and it's an easy way to pass some data, and I want to use this in the future anyway, whenever we use like compute, and I want to just say, hey, I want to pass 5 integers to compute. I don't want to be creating buffers for this. So let's do this. I wanted to do this anyway. So the way this will work is I want to create some structure that we will reflect the GPU in the same way, and I wanted to call it mesh, but we already have a structure called mesh. So that is unfortunate. Naming is hard. Let's call it mesh data, mesh draw, mesh data, mesh args, I don't know. Mesh instance. Yeah, I don't know. Let's just call it mesh draw for now. We'll figure out what it should be called later. So for now, all I want to have an ability to basically supply a transform matrix, but we are for now running an ortho projection and we don't have a matrix library yet. So let's just pass an offset and scale, right? And then we'll just transform in the position, and I guess we can do that. that's really what I wanted to do. Yeah. Okay, so we have a struct. It's like 16 bytes, super small. Now what we need to do to pass it to the shader is when we draw here, let's do this. Let's yeah, okay. So it's probably not very good to create stat vectors like every frame, but I don't care. So let's just fill this, I guess. But then, okay, yeah. So to render 100 kittens on screen, and 100 is 10 by 10, so it's like a 10 by 10 grid. So we want to do want to scale every kitten down by 10x in every direction, every dimension. And then we'll want to arrange them in a grid. So offset 0 is I over 10. And this should be a floating point division. So it's like this. No, wait. This should not be a floating point division. We should get the row where the kitten is. And this will be percent here, not division. And yeah, so this will give us numbers from 0 to 9 over 10. And then we need to do the same thing here, but it's like a row. That's the same thing. Cast to float explicitly. So this should arrange them in a grid. So that's cool. And then I just want this code to work in both paths, right? So I'm doing this like this. And then before we do a draw call, we should set the data for the draw call as this push constant thing. So there's a common set called set push, no, cmd push constants. It's a bit similar to the push descriptor stuff that we were using. But push descriptors are not in core Vulkan right now, and push constants are in Vulkan 1.0, so you don't even need, we're using 1.1, but you don't even need 1.1. Oh, you need to specify these stage flags. I think I can just, yeah, I think I can do this. So I think this is how it's supposed to work. You just say, hey, I wanna use this data, and then when you use push constants, you can say you can have separate push constants for every stage. I don't want to be using separate push constants for every stage. I just want, in the same fashion that we were doing descriptor bindings, I just want a single thing to be available to all shaders. Because in the world where there's task shaders and mesh shaders, it's easier to just not think about distinctions like this too much. If you want data, let the data be available everywhere, who cares? But then we need to pass, this is the wrong layout, we need to pass the layout that declares what stages actually use the push constants and how. So when we create the layout, we need to pass this information. I think here, yeah, there's this data that we are not filling right now. In theory, you can extract this data from this PRV blob the same way as we were doing a couple of streams ago with descriptor bindings, but I looked at that and it's really painful to do that, unfortunately. It's really painful to do that. So I don't want to be doing that. Or maybe I want to, let's see. Yeah, I can infer the stages that this thing is used for from SPRV, but I don't want to infer the size because that's too painful. So I just want to say that when you create a pipeline layout, you can pass push constant size. you get one constant block of that many bytes. We'll use it for all shaders. Let's see, so if push constant size, then we will, this thing has to be declared outside. Let's see. Oh, I can probably, yeah, I should be able to just do this, right? Hold on. Well, it's fine, doesn't matter. So you have to tell the driver ahead of time when you create the layout what stages use the constants, and also what's the offset inside the constant blob that is used by this stage. For example, if you have like 32-byte constant blob, but the first 16 bytes are only used by the vertex stage, you can say this. But I really don't want, it helps for performance, but it's painful to do this and maintain this. I don't want to be doing that for now. If one day we'll determine that it's important for performance, we'll do that. For now though, I just want to say that we use these, but I think I can infer, come on. So for now, I just want to say, what's the enum shader stage? For now, I just want to say, hey, all shader stages use this. I think this thing I can infer from sphere V. The ranges are painful to infer from sphere V, but I think the other thing is not painful. So this is mesh draw, right? And somewhere else here, same thing. All right. So now we may be passing this data to the shader, but we aren't using this, so hopefully nothing changes, okay? And no validation errors, so that's good. Now I just want to say, hey, let's use this data. So when we do the mesh, for cone culling, we will have to incorporate the world matrix into the cone culling equation later. But right now in an ortho projection, we are just moving the mesh around and scaling it. So this should not change. But yeah, so when we have like actual world matrix, then both the task shader and the mesh shader will need to read this data. Right now, only the mesh shader needs to. So let's declare the struct on the shader side as well. It is possible to, and maybe it does even make sense to do this, maybe sort of, to have some sort of macros and like include this header file in both shader code and C++ code, because we keep like ping-ponging between this and you know it's painful. The issue with that is some of these types are called differently in different like worlds, right? For example, vec4 doesn't exist in C++, uint is called uint38t in C++, align as does not exist in GLSL. You can erase some of the stuff with macros. I'm thinking that maybe we'll have to start using something like GLM anyway, so maybe we'll do that. It seems like a good idea to do this. But for now, I will just do, you know, I'll just not do that. I don't know why I'm doing, like, you don't need, I could just keep them as floats. It's probably fine. I'll just keep them as floats for now in the shader code. Alright. In fact, maybe I should keep this as floats as well. And then here, vec4 cone, vec4. Oh, but then the, oh, no, right. GLSL is frustrating sometimes, right? So I should have kept a note here. Vec4 keeps meshlet aligned to 16 bytes, which is important because C++ has an align as directive. And the reason C++ has an align as directive is because we kind of want to align these things to 16 bytes, because maybe it's important for performance. We don't actually know that it's important for performance. We should check. Yeah. I really want align as in GLSL. Maybe I should submit something to GLSlang or something. It would be so helpful to have a line S here, so that you can, right now if I do float colon4, then the size of the struct changes because of this guy, but if this had something like that, then the size of the struct would be stable to these kinds of modifications at least, and that would be nice. Yeah. Alright, anyway, so I guess for now, let's just do that and that. And now let us use this in the shader. So in the mesh shader, we need to say that we need a push constant block, and I don't remember how you do this. I guess like that. Wow, this was cool. And then block, I guess. I don't know. I have not used push constants before. Mesh draw. Own your uniform buffer in or out. I guess uniform. Okay. Yeah. So that's, I guess, how you declare a push constant. Live and learn. So then when we have our position, right now we are transforming this by this sort of pseudo projection matrix. So we will need to transform this additionally by the world matrix, right, which we'll read from mesh draw. So this is mesh draw offset 1 plus, oh, mesh draw scale, I was meant to say. Wow. Mesh draw offsets 0. I like this GLSL extension less and less because it really interferes with Vim emulation. I'll try to see if I can fix it. We were close. Oh, I guess the space is from -1 to 1. Yeah. Yeah, I mean, we can shift everything. Oh, but it's like this or something like that. Wait. Hold on. Right, yeah. Hold on. Like this, and then like this, and then like this, something like that. Alright. Yeah, and now the leftmost kitten is slightly cut off because we are moving the center of the leftmost kitten to the edge of the screen, but we should really be doing something like this, so that they are all in a nice grid. Yeah, okay. Alright, so now this is proof that we actually have more than one kitten on screen, and now if I switch to the old path, then we aren't doing this transformation yet, so let's do that there. That should be the same code, basically. Right, so we just fill one vertex instead of all vertices in the meshlet, and then we need the same push constant declaration. So that should work. Alright, so that works. So that's good. So now we are using push constants to communicate. We are also leaving spaces after lines. which is not great. We're using push constants to communicate small bits of data to the shader, which is the most efficient way to communicate really small bits of data to the shader, as long as you have few of them. So like once this is basically on some architectures like NVIDIA, it's probably fine to include like a transformation matrix here, like a real one, like 64 bytes. On AMD, it's not a great idea. But we don't care. If somebody from AMD sends me an AMD GPU, we might start to care. But we emphatically do not care about AMD right now. Okay, so that's cool. Yeah, so let's commit that. And then, you know, this should work obviously for like, let's see. There's a warning. Right, so yeah, here's a lot of Buddhas for you, and we are actually rendering all of them. So now you can see that I'm not cheating. Okay, sure. So that is good. Now the thing that I want to do is I want to automatically infer, if that's easy enough, this thing from the PRV. I don't want to infer the ranges, but I want to infer whether, right now the task shader is not reading this data, and the fragment shader is not reading this data, but the mesh shader is. And I want to be more precise about this because this can impact performance. But let's commit this first. Day 9, use push constants to supply world space transform to shaders. For now, we are assuming all shader stages use the data. Oh, the thing I'm not sure about is when you actually push the constants. Let's open Vulkan spec. Vulkan spec takes a while to load. Like a while. Like we can render a lot of triangles before Vulkan spec loads. So I'm wondering if it matters that I'm specifying. So there's two places where you need to specify this mask. Once when you create the layout and once here. I'm wondering what. So it says the stage flags must include the stages in the range. The question is, does it matter if it sort of over specifies? I guess it doesn't, because it probably doesn't. I'm hoping it doesn't really matter for performance. I'm hoping the driver is smart enough to basically look into this guy and say, like, we don't need to pass the data for fragment shader because we said that we don't here. So we are probably fine. Alright, so we will keep this as is. I don't know that this is important. It might not be, it might be, but I kind of want to try to infer this from the SPRV, because we already have a SPRV parser, and we said that we are going to extend this to do more things for us. So this is one more thing that we may want to do. Let's see. So let's disassemble our mesh shader is kind of large. Let's disassemble our vertex shader. That also now uses the push constants. Yeah, and see how they look. So basically there's just a variable. Oh, there is a variable with a storage class push constant. We already track all of this stuff. This should be super simple. Let's see. So if you are confused as to what we will be doing like right now, you can refer to the stream where we did spear reparsing. That is called, I think, spear reparsing. Yeah, so we already parsed all kinds of information out of spear-v, and we already parse all of the variables out. And we already say, hey, for all of the variables, if some of them are uniform, record this here. So I guess we can just say, hey, do we use... And I kind of wanted to do this thing as well. This will be important for uniform buffers, maybe. Or maybe not. Not clear. Okay, yeah, so... Let's just say bool uses push constants, right? That's it. Like, the correct thing is to look at this variable and then to infer the size of this. But the problem is the size is very hard to compute in spear-v. Like, it will take an entire stream to accurately compute the size of every possible thing in the spear-v shader. So we'll just record a boolean that says, do we even use this? Are we like zero initializing stuff somewhere? How does this thing work? I guess we are. Storage class push constant. Shader uses push constants true. Oh, this assertion was wrong, by the way. I hit this before. Let's just remove it. This should be to do. We currently assume that I prefers to pointer. Yeah, okay. Yeah, I think that's it. Probably. Oh, what is this? Wait. Oh, we did this in parse shader. Okay. So now, in here, we should be able to go over all shaders like this, and then say if shader uses push constants, tell about this to the driver, and that should be it. Let's see if we did this successfully. There's only one shader stage, and this is one. Oh, this is the vertex shader workload, right? So this mask corresponds to the vertex shader, and then in the why did we hit it one more time? There's no loop here. It's odd. Okay. Is this breakpoint like... Okay, the breakpoint... I think when I set the breakpoint here, it actually set it like after each loop iteration or something like this, which is odd, it shouldn't happen. But yeah, so there's only one bit set here now, and it should refer to the task shader, rather mesh shader. Oh, maybe not. Maybe we didn't actually do this right. Let's see. What? Okay, maybe we did not do this right. Do not contain stage flags. What? No, wait. What? Oh no, sorry, this is different. What? Oh, I think it's telling us that we cannot pass all in there. Oof, that's unfortunate. No, wait, hold on. The valid usage says for each byte, stage flags must include all stages. No, hold on. I think this is fine. I think we are doing things correctly. Let's see. Why is this doing an exact comparison? Isn't it wrong? So what the validation layers are doing is they're saying, hey, let's find all of the stages that are using let's find all of the stages from pipeline layout that are using the push constants in that range. And then let's do an exact comparison with the stage flags that we pass. And then if they didn't match, they say, hey, here's the bit mask for stuff that didn't fit. But I think isn't it backwards? It says stage flags must include all stages for all flags that we have declared in the layout. It does not say. Oh, is that the problem? Hold on. Oh, never mind. Yes. Yeah. Okay. Never mind. Validation layers are correct. Are correct. So we cannot. Okay. Damn it, this is a problem because this is the point where we need a wrapper around some of the stuff, because we don't record this right now. This is the point where we need to have a struct that has this, and some flags. Because this is just not tenable. Yeah, wow, okay. Okay, I wanted to do this before, so let's just do this anyway. Come on. PK, CMD, push. So right, so basically this has to be an exact mask. Okay, so for now let's just say task bit here. Oh, not task bit, like mesh bit. And then here we will say vertex bit. And that should, alright, so now that works. But that is the thing that I wanted to avoid. So we need a solution to this problem. Day 9 infer push constant masks from shader stages. Fortunately, this required us to hard code the masks in the C++ code that calls push cmd push constants. We'll fix this shortly. So yeah, so basically we are beautifully computing the mask automatically here based on the exact stages that use this push constant block. But we have to pass the exact same value pretty much here. Otherwise, we would be violating this rule that says for every bit that we are specifying, the layout must include that, which is slightly redundant, but you know, we kind of have to deal with that. So to fix that, let's introduce something called program that we will be able to create from a bunch of shaders, and that will contain two things that we are already using, which is the pipeline layout, layout, the descriptor update template, update template, and this thing that we need now apparently, which is shader stage flags. Push constant stages or something like this. And this will replace these two functions. We won't really need to be calling them directly, but for now let's just have a separate thing. So I guess we will do this. So you pass a device, bind point, a list of shaders, and then push constant size, and then we'll do destroy program, usually we do these things with a boolean return, but I'm kind of tired of checking this boolean, so this is fine for now. So this will just simply delegate the work to the other functions, but I guess here we will, yeah, that's fine. All right, so all right, fine. So yeah, so we will just encapsulate. The reason why we are doing this is just because I want this extra stage mask around, and I don't want to carry it with me all the time. Like compute it manually in the C++ code and then refer to that, and this just gets error prone. So let's just say program layout is create pipeline layout, device, shaders, push constant size, and then program update template is create update template, and device, bind point, program layout. And then for this, for now, we will use the same code that we just used here. Basically a program push constant stages. Destroy program just calls destroy pipeline layout. And update template. All right. And now let's just refactor our code to use this thing. Our C++ code will become shorter, which is nice. So we don't need these two separate entities now. Oh, I guess I should do... I mean, we have like redundant assertions everywhere. The reality is these guys shouldn't really fail ever. Like, if these fail, it's a program bug. It's never a... or a driver bug, but it's never a legitimate error that could happen. So there's that. So we don't really need like correct error checking for this. So now we can say that mesh program is created from, it's kind of the same stuff that we have been passing to these other functions. So it's a graphics pipeline, it requires two shaders, and it requires push constants, and we don't need to assert anymore. And then we do mesh program RTX. I have been told by several people that RTX is a confusing name, because RTX refers to the ray tracing thingy, not to the stuff that we are using that feels just as exciting as ray tracing. What do I know? We might refactor our code at some point to remove the suffix. I do not want to do this now. Right. Alright, and then here we do mesh program layout. We could like embed this thing as well in the program, but I don't want to do this yet. We might do this at some point, but I don't want to do this yet. Because who knows, it might be that we need like multiple graphics pipelines from the same pair of shaders because the states are different. It's not quite clear that I want to do that. And then it stops being a program and it becomes a pipeline. Because this thing is not dependent on states really, right? It's just the set of shaders essentially. So yeah, I don't want to do that yet. Alright, so now when we destroy stuff, we just say destroy program. And then here, this is similar to in OpenGL, there is a concept shader program that is not the same as Vulkan's pipeline objects, but it's similar to the thing that we have just created. To the monster that we have just created. It's not really a monster, it's a small nice helper. Alright, so mesh program RTX update template, mesh program RTX layout. And you know, now like with this program in theory we could abstract some of this in a helper function, like maybe this should have a helper that just passes these guys directly, I don't know. But I want to build the minimum amount of abstraction that we need possible. Like I'm not building, you might have noticed, I'm only building abstractions when our life without them becomes painful, right? Which seems like the correct way to program. It also seems like a very different way from how a lot of people program these days. But that's a rant for another time. Alright. And the reason why we did all that is that now we can just do mesh program RTX push constant stages here and mesh program push constant stages here, and our code should be validation clean and perfect and everything, right? And now when we change shaders, all of this stuff will just work. So that was good. And the only real issue is you have to pass these as separate objects when you call like push constants or something, which is why it might be helpful at some point to build a small inline function that just helps call these guys. But I don't want to do that now. Okay, so that should work. We should commit that. Oh, the other thing though is now we don't need create like the other things. Now we don't really need these functions, they can be just internals. So maybe what I want to do is I can keep this one, delete this one, create. I want to make everything here that we are not exposing internal. So this should be internal, aka static. And I want to move all of the non-internal functions here. So this now can be static, this now can be static, this is already static, this is already static, and then we are doing this computation twice, which feels weird. So let's just pass this here, wiki shaders, stage flags, push constant stages. And then when we call this here, we can do the same thing. Alright, so now we have a smaller interface for the shader stuff, right? Because you can create program, destroy program. You don't really need layouts and templates like in as separate objects. And we could sort of pass something to this guy. We still need, yeah, like this interface could be nicer at some point. But for now, there is no real need for it to be nicer. So let's keep this as is. All right, D9, add program object. Program encapsulates a set of shaders and creates all necessary objects, basically, right? That could be created without knowing the full state. When you create a pipeline object, you need to know the blend state, the depth state, and all of that. Program doesn't need that. Like, we could be creating a compute shader, compute pipeline state with the program, but not the graphics program. In fact, it might be a good idea at some point to embed the compute pipeline object in that. Just to correctly pass a non-hard-coded push constant stage mask. The only issue is now that if no shader needs the push constants, then I think it's invalid to call this thing with 0. So I think technically what should happen is it should be like if mesh program push constant stages. But we will cross this bridge whenever we hit an error like this. It seems weird for me to have this in the spec, but maybe that's fun. Maybe that makes sense. All right. Okay. Yeah, so now we are drawing a bunch of kittens on screen. And with push constants. We will stop using push constants probably for this tomorrow, because I want to start using like, probably not instancing, but like drawing direct or something like that tomorrow. But for now, this seems fine. In fact, maybe we don't really need the perspective projection matrix and all that, because we can already render a lot of kittens. So maybe we just spend tomorrow on making this very fast. That would make sense. Alright, yeah, so that's basically what I wanted to do today. It's been 2 hours and 10 minutes. And mission basically accomplished. So unless somebody wants to ask any questions in chat on whatever we did today or whatever else people want to ask questions about, then we'll just end this slightly earlier. The streams usually take like 2.5 hours, but it's usually because I want them to take 2 hours, but then, you know, things happen and they take longer. But today things happened, but we managed to get through them quickly. So that is good. And now we can render, especially if we enable vsync, disable vsync. Oh, now it renders. Now our Buddhas are slightly smaller on screen, which I guess means there's less work for rasterizer a bit, because some triangles are called earlier by the rasterizer zero area triangle calling. Alright, so now we are, okay, so then mission definitely accomplished, because we are rendering 21 actually, billion like 20.7 to 20.9 looks like, billion triangles per second, with mesh shading pipeline, compared to a measly 7.4 billion triangles per second, right? This is what NVIDIA should have been advertising, not ray tracing. Well, ray tracing is cool, maybe. Who knows? Should I rename this RTX stuff while we are at it? Let me rename the RTX stuff while we're at it, and then we will end the stream. Yeah, so the correct name, I guess, is mesh shading. It's such a long name. Like, in all of these places it's fine, but like, mesh program RTX, what am I supposed to call this? I guess I can just call this mesh shading and call it a day. Alright, you know what? Sure. We're more verbose, but more correct. I will come back to these guys in a second. This needs to be split into multiple lines. Alright, and yeah, for these capital suffixes, we'll just use MS. I didn't want to do this because MS stands for mesh shader, and we already use the suffix MS in the mesh shader. But since there's like qualification like pipeline and program, it's probably fine. Hopefully that will make, you know, people who think RTX is ray tracing, which it is, happy. Yeah, so that's just basically code cleanup. Now we don't have a single RTX here. You can only run this on an NVIDIA RTX card. However, in theory, AMD could support, you know, maybe like some other vendor in theory could support NV mesh shader extension. Nobody prevents them from doing so. I don't know to what extent. Like, I don't know how close your GPU has to be to an NVIDIA GPU for this to actually work, right? But in theory, this could happen. Oh, and this vsync again. Vsync. But yeah, that's kind of all I had. Chat is awfully silent today, so I will assume that we are done. RTX to mesh shading or MS to avoid confusion. Yeah, when I tweeted the the performance numbers that I was playing around with and was like really excited about this. You know, tweets are limited by, what is it, 280 characters these days, right? So whenever you want to tweet anything interesting, and you can split the tweets, but it's like less readable, and it's like worse for a number of reasons. So you try to compact these as much as possible. And like, I'm trying to communicate a lot of information in a really short tweet. So I'm like, whatever, I'll just assume that people have seen the streams and know that we are not using ray tracing, we are using rasterizer, but we are using a feature that's available in RTX cards. And I said something in the Twitter about like the pipeline, the RTX pipeline that we were doing on using on streams or something. And of course, some people assumed that this was ray tracing, and we're like, yeah, of course you can render a lot of things with ray tracing, because ray tracing is less sensitive. A lot of triangles with ray tracing, because it's less sensitive to triangle counts. So as long as you have a lot of instances of the same thing or something, it's like less bad. I'm like, no, I'm not using ray tracing. I'm using mesh shading. Mesh shading is awesome. I don't have an opinion on ray tracing because I haven't used it. Alright. So yeah, that's it. Any questions? No questions. Then we'll just call it a day. Thank you for being on stream. And tomorrow we will be trying to, so right now, as I mentioned, when we are rendering like Buddhas, we are rendering, well, without vsync, whatever, like basically 20 billion triangles. And when we are rendering kittens, we are, oh, wait, I thought this was worse. Oh, I guess when we're rendering 1,000 kittens. Interesting. Huh. No, okay. On kittens, on 100 kittens, we are also like 18 billion triangles per second, so almost 20. Not quite 20, but almost 20. So maybe we are not doing that bad. But I kind of want to render more. Like, what I want to do is I want to say, hey, is that too much? Nah, that's fine. Like, here's what I want, right? Oh my god, 24 billion triangles per second. So maybe we're already rendering things pretty well. Okay. Okay. But point being, tomorrow we will start exploring ways for us to render the same picture, which is it does something weird to my eyes, where if I look at this, the kittens persist. So we're rendering like 10,000 kittens right now at, what is it, 80-ish FPS. So that's like 800,000 kittens per second, which is pretty nice. I was hoping to get to 1,000,000 kittens per second, but it might be really hard without like occlusion culling and kittens actually occluded. But I want to do the same thing without doing 10,000 draw calls. And I want to do this in both pipelines without doing the 10,000 draw calls, and you need a bit of a different approach to these. So this is what we are going to be doing tomorrow. And then maybe depth buffer or something. Alright, thank you. See you guys tomorrow. Let me stop the stream.